Hi guys, in this video I'm going to go through the free response question on the pendulums. It is marked on your worksheet as number 2, and quite honestly that's because I copied and pasted and I forgot to change the numbering, but that's the number that we are looking at. It's the one that has this diagram with it. So on this problem, I want to talk about a couple things that you will need to be careful with the AP test, as well as go over the whole problem. But one thing is on your free body diagrams that you need to be careful of how long your arrows are, that they need to be the correct length. In this case, the tension arrow should be longer than the gravity arrow for a couple of reasons. One is that it's the hypotenuse, like this piece right here should equal the gravitational force here, okay? Which brings up another point is on your free body diagram, don't draw those dotted lines. Sometimes we put those in class because I'm explaining how things happen, but on your test, on the AP test, just leave your free body diagram completely open like this, just like as clean as possible. You've got your vectors, they are labeled, and that's it. But the tension does need to be greater than the gravity. Another reason that the tension is longer than the gravitational is because it's also the centripetal force, right? That's what's causing the centripetal force. And so let's just keep in mind that we do have a centripetal force going on. And let's not forget that, because that tension is what's providing that centripetal force. Okay, and I bring that up because I want to take a look at the next problem, and it's going to deal a little bit with that. So when it is in motion at its lowest point, okay, here it is at its lowest point. It is in motion. Let me go back to what I was talking about a second ago, a couple things. Let me step back. First of all, your tension needs to be longer than your gravitational. Why? It's not moving in an up and down direction necessarily, but this tension is what is providing the centripetal force. And so because of that, it has to be longer. If they were the same length, then that bob would not be moving. It would just be sitting there, right? But it is moving, and so therefore the tension has to be longer than the gravitational force. Let me mention one other thing. I know that the test this year is going to be a little bit different, but if you are writing something or drawing something and your drawing is just not very clear, or your graph, you made a graph and it's just not a beautiful graph, you can always make a note to the grader. So if I drew this and it just was kind of messy and you couldn't really tell, you can write a note like this and kind of explain to the grader what's going on. Sometimes that would help. Same thing here. These two, they look awfully similar, but you might write a note to the grader saying that the force of tension is greater than the force of gravity. But this centripetal force, I wouldn't put that on there because your free body diagram needs to be as clean as possible. Okay, this next question is actually an energy question. Remember, when we did our LOL diagrams, the potential energy, gravitational energy, gets converted over to kinetic energy. So let's talk about a couple things. If we are calculating the speed of the bob at its lowest position, we're going to go back to this LOL concept, set the gravitational equal to the kinetic energy. Formula for gravitational is mgh. Formula for kinetic is 1/2 mv squared. If we are going to solve this, because what we are looking for is we are looking for v. So if we're solving for v, my m's cancel. Now, how am I going to solve this for v? I'm going to multiply times 2 so that I get 2gh. And then I have a v squared over here. Well, I can just take the square root of that and I get this equation. And when we were studying this the first time, this is an equation that is helpful to memorize. You don't have to, but it would help save a lot of time when you did that. Okay, now that we know that v is the square root of 2gh, I just have to plug in what I have. So I know that gravitational, and on the AP test, you can always use 10 for your gravitational. And then the height, was that given to me? I'm going to scroll down here and see. It is given to me. It is 0.08 meters. And so I'm going to multiply that out and get my final answer, and the answer is about 1.25 meters per second. Which brings up another question, what about significant digits? Remember on the physics test, we are not as obsessed with significant digits as they are in chemistry. You do want a reasonable number of significant digits. So I wanted to keep that as a reasonable number. Okay, you could have 1.3 because I think for sig figs, 1.3 is actually the correct sig figs. But again, we're not real picky on that in physics. I stick with 2 or 3. You guys, I made a mistake here. This 2 is not supposed to be outside like that. The 2 actually needs to go inside with everything else. And so when I do that, I will still get this answer. But I want to let you know that that was a mistake. So what you really should have written here is you should have the square root of 2 times 10 times 0.08. And that should come out the same, but I put it on the outside. Please put that 2 on the inside. Okay, the tension in the bob at the lowest point. I do want to mention that I misspoke on a recent video, and I said that the only force here is the force of tension in the string, which is true, but it's not an equilibrium here. And that's kind of what I was talking about on the other page, that we have this force of tension and we have a force of gravity. The force of tension is the centripetal force, and it is greater than the force of gravity. If they were equal, it would be sitting there and not moving. It's not equal. There is a tension, and so it is greater than the force of gravity. I bring that up because if you had looked at this question and thought about this at its lowest point, if it was static, that is, if it was sitting still, you would just say the force of tension is equal to the force of gravity. But it's not still, it's moving, and so that there is a tension there. And so we do have to do a little bit more calculation than just mass times gravity. Okay, well, what is the net force? Well, the net force is the force of tension minus the force of gravity, because they're both going in the y direction, but the force of tension is greater, and so the net force is the tension minus the gravity. The centripetal force, we have a formula for centripetal force. It is mv squared over r. And I might take a second right here to remind you that that actually was not on the sheet either, that we have the centripetal force is mass times the centripetal acceleration, but centripetal acceleration is v squared over r, so centripetal force is mv squared over r. That was another one, kind of like this one here, that if you memorize it, it just makes your job a lot easier. You don't have to go through and derive that every single time. So I remembered that centripetal force is mv squared over r. Okay, let's go back to our equation. What we are looking for is the tension in the spring. That's what we're solving for. Let's go ahead and add the force of gravity to the other side so that we have the force of tension is the force of gravity plus mv squared over r. So now we have force of gravity is mass times gravity, and then adding mv squared over r. If you wanted to factor out that m, you could. You can't cancel it because there's not an m over here on the left, but you could factor it out if you wanted to. I'm just not going to take that step. I think I'm ready to start plugging in some numbers. Okay, it's not pretty, but we have mass times gravity plus mv squared, and that v is the v I got from here, over r. And the r was given in the write-up of the problem. So again, it's not pretty, but I have everything I need. So now I'm going to go ahead and do my calculations. Okay, your force of tension is 0.93 newtons because this first part, the mg, was 0.85 newtons. The centripetal was 0.0889 newtons, and our tension then is 0.93 newtons. One thing to notice, the centripetal force, back to the question we had the other day on where is the centripetal force the least. Look at that. That's a pretty low number. So that is the least where the centripetal force is going to be the least. The centripetal force on the edges is going to be much greater. But here is the lowest point, and that is where the centripetal force is the least. So we add those up, we get 0.93 newtons. Next part is one modification that can be made to double the period of oscillation. So remember that we have this as our formula, right? How could we change this where the period would be doubled? Well, the easy way that I see, the only way that I see, well, there's a couple, but one that I see is we could multiply the length by 4. So if we multiply that length by 4, that would double the period. Another way to do it would be maybe mess with the gravity, like take it to a different planet. That would maybe do it as well. But this is the easiest way that would come out. Okay, that is problem number 2. I will do a separate video for number 3.